Our next speaker is Kyle Barron. Kyle is a software engineer at Development Seed, where he builds open source tools and infrastructure that process and visualize geospatial data. He has expertise in cloud-native geospatial vector data formats, speeding up Python and JavaScript applications from Rust, spatial indexes, and efficient data pipelines. He holds a BA in economics, minoring in mathematics from the University of California, Los Angeles, which he earned in 2017. Kyle previously worked as a software engineer at Unfolded and then Foursquare, building browser-based geospatial data visualizations on the web for vector and raster data.
Awesome. Well, thank you. I'm happy to be here. It's been an awesome conference so far, so hopefully we'll continue that. I'm Kyle, and I will be talking about Lonboard, a Python library I developed for fast, interactive geospatial data visualization. So really, we have three goals with this library. We want it to be fast, we want it to be simple and easy to use, and we want to use interactivity as much as we can in this Jupyter paradigm. So why not use existing libraries? What is there that we need to create a new library for? So IPyLeaflet is a really common library that a lot of people reach for rendering vector data, like points, lines, and polygons in Jupyter from Python. And it's good for a lot of use cases. Up to here, about 300,000 points. It can handle that. It takes about a minute once you get to 300,000 points. I tried with 400,000 points and the browser crashed, so there is some limit. There's also another library called PyDeck. That PyDeck, instead of Leaflet, uses WebGL GPU-enabled rendering in the browser, and so it's able to handle a bit more data than IPyLeaflet was able to. But above 1 million points, it still failed, and that still took over a minute to render those million points in Jupyter. Here's Lonboard. We had to make the line not black so that it wouldn't blend in with the axis. Lonboard is incredibly fast compared to IPyLeaflet and PyDeck. And believe it or not, it keeps going. That was cut off where IPyLeaflet and PyDeck failed and couldn't render any more data. But here, it's able to render 3 million points in about 2 seconds. And here, if you don't believe me, is it in a GIF? It's small enough to put into a GIF. Here, this is a GIF of a geodata frame with 3 million points, where every one of those points is given its own color of a dot. Every one of those points has its own radius. And all of that happens from GeoPandas to the browser to the visualization on the GPU in 2.5 seconds. And this is really interactive too. So once you render, this is an interactive map. It's not a static PNG or SVG. You can zoom in. You can get a tooltip over your data. And it's a big improvement over some of these existing libraries in terms of speed, at least. And actually, the graph keeps going. So here, I tested it with 15 million points. This is on my own laptop. And it is laggy, but it is functional at 15 million points. So here I was like duplicating the data set a couple times so that I could get up to 15 million points. Once you zoom in, you're rendering less data. It is able to render a bit better. But this is GPU dependent on the client machine. So here I have a recent MacBook, and it can handle about 10 million points pretty efficiently. I know people who have desktop gaming computers with really nice GPUs, and they've been able to render like 50 or 60 million points. But at whatever hardware you have, there's almost certainly some sort of GPU, even if it's integrated in your own laptop, and you should be able to render much, much more data than what IPyLeaflet or PyDeck did before. And so that begs the question, like, what am I doing differently? How is this so fast? And for that, we really have to talk about JavaScript. I know it's a Python conference, but JavaScript is necessary here. And so there's three parts of rendering vector geospatial data in a web map, and each one of those we can improve on. So you have to load data into the browser somehow, you have to manage it in memory in JavaScript, and you have to render that data to the screen what the user actually sees. Historically, you'd use GeoJSON, GeoJSON-like objects, and something like Leaflet to render data in a web browser. Each of these points has some downsides. GeoJSON is really, really slow to read and write. It has a massive file size. So when you're copying from Python to the browser, especially if the Python session is remote and it incurs a download essentially to bring to your browser, that slows down the visualization a ton. If when you're parsing GeoJSON, you have to parse into these JavaScript-like JSON objects. That has a lot of memory overhead. There's a lot of performance overhead on the JavaScript side with creating and destructing all of these tiny objects. It can't be shared with web workers or WebAssembly. It has to be, again, coerced into a different format if you want to send it to the GPU or something like that. And then Leaflet has to iterate over all of these small JavaScript objects, render them each individually using, in its case, HTML canvas, and that's pretty slow. So instead, we can use binary data at each step of the process and make this a lot faster. So Lonboard is loading data to the browser using GeoParquet, which is really, really efficient in its compression, and also has some nice features like it's cloud native, so you can read portions of the file without reading the entire file. Once it's in memory in the browser, it uses a Rust WebAssembly library that I developed to parse that Parquet data into Arrow. And then Arrow in JavaScript is binary, so it can be copied directly from WebAssembly to the GPU without even making a copy into JavaScript. DecGL is the third piece of this puzzle that allows us to have a binary API and a binary interface to pass the data directly to DecGL so that I'm not creating my own GPU visualizations at the draw level, so to speak, the GPU level. I'm using this existing library that has been around for 6 or 7 years, was originally developed by Uber. But by being binary at the entire step of this process, we can make each of these steps like 10 times faster. So taking some input format, like a GeoPandas geodata frame or DuckDB, we can convert that under the hood in the Lonboard library to GeoArrow. GeoArrow then passes that to this AnyWidget library that Trevor Manns is developing and had a talk about yesterday. That simplifies the process of getting data from Python into JavaScript. We serialize this to GeoParquet so that it's smaller over the wire, which means that in the case where someone is working on a remote environment like Jupyter Hub, doing this visualization incurs this download from this remote server environment to their machine. And when we compress it as GeoParquet, it's much smaller, and the download speed is much faster. On the browser side, we're able to parse that back into GeoArrow and pass that from AnyWidget's JavaScript side to DecGL to the GPU, and all of that happens incredibly fast. But I want to be clear that all of that happens away from the user. And so it's intended to be really simple to use. So the primary API that most users will interact with is the GeoPandas or DuckDB API. You can pass in any one of these objects in these very common Python libraries into Lonboard, and it'll handle this conversion into GeoArrow under the hood so that users only have to think about what they actually want to visualize and not the technical bits. So here, for example, this is we have plenty of example notebooks in the documentation. This is a DuckDB query where this is querying directly on a Parquet file in some object storage. we pass in some queries, and we can call heatmaplayer.fromDuckDB, just pass in the SQL string, pass in the connection, and that automatically generates this heat map from these million points through DeckGL. Also, if you're using some other non-Python libraries like GDAL and doing stuff on the command line, you can pass data into the Lonboard command line interface, which accepts any GDAL supported file format. It'll load using the latest version of GDAL that allows direct to geo arrow loading. So this is a pretty big shapefile, I believe, that can render in like half a second. This actually creates a standalone HTML file. So you can pass this HTML file to somebody else, and all of the data is self-contained. There's also an API from Python to take whatever map you have and export that to an HTML file. So you can iterate, explore your data, apply some sequence of rendering parameters to get the data how you look like, save it to an HTML file, and just send that HTML file to someone else, and they'll be able to open it and see the same visualization you have. Note that it does save the data encoded in the HTML file. So if you're working with 100 megabytes of data, the HTML file will be 100 megabytes. And there's a lot of potential with Jupyter widgets, and especially being based on any widget, that allows for really interactive exploration. So when we are creating this widget, we use this reactive interface that allows us to update portions of the rendering without sending all of the data again. So here, we've already sent the geometries to begin with, and then if we want to change the rendering parameters here, which color map we use for the points, we can do that only by sending this small NumPy buffer of the color for each point without sending all of the data to start with. There's also really cool interactivity we can do on the GPU. We can send all of the points. Here, I guess so far all the examples have been points, but we work with lots of different data types. And we send all of these points to the browser, and then on the GPU, we can use a numeric column to filter the data on the fly. And so here, this is about 2 million, I believe, points from an air quality data set where we want to see what regions of Houston have the worst PM 2.5. We could also filter by the time of the day. And then you can easily look at the spatial distribution of your data, see, oh, there's the data that has really bad air quality. Let's look into that data more. You can also plot polygons and other types of data. This is an example from the Overture buildings data set that brings, it's a really large GeoParquet data set in the cloud, but it's possible to bring just a portion of that really quickly into your Python notebook. There's an example notebook of this where GeoParquet lets you fetch just the data in New York in 10 or 15 seconds, even when the entire data set is like 2 billion rows. The underlying DeckGL library has lots and lots of different layer types. So here, this is the arc layer type combined with this extension that lets it only render what's over the cursor. So this is looking at county to county migration, and you can see, you can really interactively explore your data quite well with a bunch of these different layer types. We also have integration with a lot of different Jupyter widgets. So this is some integration with Shiny. We also have some integration with Panel. And this, it's designed to make it really easy to create some dashboard applications from whatever Python examples you have. I do want to mention also, because everybody asks, like, what is Lonboard? Like, that's a crazy name. Well, DeckGL, the underlying JavaScript library, a deck is a part of a skateboard that you ride on. And what's a geospatial skateboard? A Lonboard. Yeah. So that's why it's the name. I want to talk a little bit about some future work. So far, everything in Lonboard has been more efficient than stuff like IPyLeaflet, but it still sends all of the data that you pass into the Python API to the browser. And that means that eventually your GPU will get saturated and you won't be able to render more data. But I'm working, hopefully in the next 6 months, of adding some of these APIs to allow you to pass in lots and lots of data into the Python side and only render what you actually care about into the browser. And so here, these are a couple Rust-based Python libraries that I've ported from original Mapbox implementations in JavaScript that do hierarchical clustering of point data and archery indexes of non-point data. This allows us to have a really smart relationship between Python and JavaScript. So as you're zooming around the map, it only selects and renders that portion of the data without sending all, say, 100 million points to the browser. We've also been doing some initial work on trajectory data, of movement data. So here, this is an animation of ships moving around the eastern seaboard. This is like 100,000 ships, and like each of those ships have 100 or so time steps. And DeckGL has this awesome thing called the trips layer that allows you to plot a line string, but only view the portion of the line string over time as you animate based on the current global time. I've still been working on some of this API with moving pandas and with other trajectory data libraries. So if you happen to be using trajectory data in your daily work, come talk to me. I'd love to talk a bit more about how to make this easiest for users. And there's also a lot of potential in using GeoArrow outside of the visualization side. So GeoArrow can be used for analysis and for integration into a lot of different libraries. And here, this is an example in this GIF of loading from a Parquet file on disk into Rust, into Python, into then C, into Parquet, into the browser, into WebAssembly, into JavaScript, into the GPU. And so this is in the geospatial track, but it could also be in the plain, nice scientific programming across languages track. That GeoArrow is really the core of Lonboard, both to make it really fast for visualization in Lonboard, but also to be a cornerstone of this upcoming GeoArrow ecosystem to make it really easy to play nice with all of these different libraries, query engines, new spatial support, and stuff like that. That's it. I can pull up. I have a little bit of extra time. I'll stop for questions, and then I can bring up a quick demo if there's still time.
All right, we'll go ahead and open up for, yeah. Otherwise, do you want to do the demo now before we open up for questions? You got time.
Sure.
Oh, yeah. You still have, like,
I know.
7 minutes. So
that was a little fast.
Oh, you're good. Demos are great. And then you'll still have 5 minutes for questions after that. So.
Yeah, so let's, this is when I really wish I was, awesome. So this is actually I'm going to change to mirroring because I cannot see this. Let's bring this up. So this is an example of using the scatter plot layer on speed test data. This is what most of my default images are from. This data comes from the Ookla data in the AWS Open Data Registry. So here, this is point data across the globe for how fast internet speeds are across the world. We can load all of this into a geodata frame. Here, this is a point and date and download speed in kilobytes per second. You can pass just the from GeoPandas method to create a visualization from a geodata frame. So this is using the scatter plot layer, which is the layer type that renders points, and pass that into a map object. Now here, this renders, but it's all in black. It's not very interesting. We can change this get fill color attribute to change how the points are rendered. If you just run that cell, now all the points are in blue. That's better than black potentially, but it's still not very interesting. So instead, we can take one of the attributes in the data set. In this case, it's just the download speed. We can construct here, this is a normalized download speed from 0 to 1, where we're linearly converting the download speed from 5,000 to 50,000 kilobits per second to this 0 to 1 metric. We can take some matplotlib color map, such as this, and then I have a helper that applies this color map onto your data for you, and we can set that onto this getFillColor attribute, and voila, we see that all of these points have a different color based on the download speed. And any of the attributes that start with get are ones that you can pass a column of data to instead of just a scalar value. And so here, we're using the same source data to pass into getRadius to change. Now, every point has both a different color and a different radius. So we can zoom in somewhere and see the larger circles are both greener and have faster download speeds. I do also want to point out, I think it's in here, oops, that it's really annoying to scroll up and down every time you want to see your visualization. And so there's this awesome package if you're in Jupyter Lab called Sidecar, and that allows you to plot your map on the side of your notebook. So here, this is using, oops. And I'm actually going to reload the page. So here, let's just kind of run through this quickly. This creates this sidecar object on the right side, and then plots this scatter plot layer and displays it into this sidecar object. So now we have here, this is vehicle parking infractions or some sort of crime statistics from Chicago. We can pass this into the sidecar object. And now, similarly to before, we're like, this is just black points. It's not very interesting. Let's take some aspect in our data, say, how many days has the vehicle been reported as parked? And similarly, we can run through this and really interactively see how our data is laid out, because we can see our code on one side and our outputs, this map, on the other side of the notebook. All of these examples are on the repository. They should be, as long as you have Sidecar installed, they should be pretty easy to run. But I think that's a good place to stop for questions.
Alrighty, we'll open up for questions. Also encourage anyone online to go ahead and post those to the thread. We're going to read one of the online questions first. So Kevin Tile asks, what makes a parquet file a geoparquet file? Is it as simple as adding a geometry column to it?
The easiest way is if you save it with something like GeoPandas or some other geospatial library, there's a little bit of metadata at the end of the Parquet file that signifies it's a GeoParquet file. It means that the GeoParquet spec doesn't have to create something new. It only adds some metadata into a Parquet file, and that means that any Parquet reader can also read these GeoParquet files.
Not that I would ever do this, but I have 500,000 trajectories sampled at 3 seconds for a month. Can
That's
I
a lot.
plot? Yes. Can I? How many agents? How many of these trajectories can I plot before things crap out? Depending on assume standard hardware.
Well, the easy answer is that the PR isn't merged, so you can't do anything yet. At the end of the day, this is all running on the client GPU. And so if you have 500,000 line strings sampled at 3 seconds for a month, like you can't visualize all of that at once in a normal GPU.
I meant the animation, an animation.
Well, the animation still works by loading all of the data into the GPU and then just selecting which part of it actually renders. So it's still bottlenecked by the full data size, even if you are even if it's long animations, if that makes sense. But yeah, that's something that I want to get merged soon.
Okay, I'll find you afterwards.
Okay.
Any other questions? Oh, we got a few.
So if for better or worse, shapefile is really ubiquitous. What's like the most direct zero to hero way to use shapefile with Lonboard?
Here, let me make this a bit larger. There is a CLI, and so if you have a CLI, you can just pass a shapefile path into this CLI, and you'll be able to make a map. Otherwise, I'd say use the GeoPandas read file command. It's easiest today to go through GeoPandas, and it's really stable. But with the latest advancements in Pyogrio and GDAL having arrow support, as long as you pass use arrow equals true into geopandas.read file, it's really, really fast to read from a shapefile into GeoPandas.
Thanks.
Thanks for the talk, Kyle. You mentioned dashboard integration with panel. I'm just curious, just so I understand completely, but do you see this Lonboard like a 100% replacement for something like Data Shader? Are there any feature differences?
So I do have an awesome part of this of the website that talks about alternatives, and so it's not, at least today, a competitor to Data Shader, because Data Shader handles really any size of data that you pass into it. My understanding is that on the server side, it'll aggregate all of that data and plot that into a usually static or interactive, but like server-side rendered image. And so I think potentially in the next year, if we have some of these good scalability improvements, that we might be able to, for some use cases, be similar to Data Shader. But it still requires that you're connected to a browser, and so requires that you're in Jupyter. But Data Shader is also a great library, so it's not one or the other.
So we have another online question. So any plans to include raster data for interactive visualization?
Yes. It's also in the works for the next 6 months. We are exploring some integration with like ZAR and DecGL, exploring some raster visualization. The exact scope of what that looks like is not quite certain yet. We do have a bitmap and bitmap tile layer. So if you're using some server-side rendered tiles, like from potentially Earth Engine or from T-Tiler, a raster tile server that development seed builds, then you could pass that into the same Lonboard map and have vector data connected with raster. But this isn't kind of rich client-side rendering. It isn't. It's just rendering the PNGs, if that makes sense.
Great. Any other questions? Yeah.
Thanks for the talk, Kyle. I have a question on client-side rendering, basically in JavaScript. Sorry, it's
Yeah.
Python conference,
Yeah.
but yeah, can we render the large amount of data on map libra or mapbox in the JavaScript API?
So right now what happens with Lonboard is that we are rendering DeckGL in conjunction with MapLibre because MapLibre is really good at rendering a base map. It means that it renders all the text labels, all the outlines of polygons, of boundaries to make it easy to understand where on the globe you're looking. But MapLibre doesn't have a binary data interface, so we can't pass in data like we can with DeckGL and get as efficient rendering from GeoArrow. So today, rendering together, Lonboard also has JavaScript APIs. So if you are a JavaScript programmer and you're building a web app, you can get the same performance from Lonboard directly in the browser, but that's a little bit harder to use today because you have to make sure you have the right format of GeoArrow to pass into the browser, whereas Lonboard simplifies this because everything under the hood makes sure that your arrow layout is correct on the Python side. Yeah.
Awesome. Thanks so much.
Awesome.